All right. Give it a couple minutes before we get started. All right. Get going. Maybe one more minute. Maybe we'll just once I finish writing out the sentence here on my screen. Let's put it this way. Okay. Yeah. So, brief recap of last meeting, which was 2 weeks ago now, since I had to cancel last week. So I think that the main thing we covered was univariate Lagrange interpolation, and here the task that this refers to is the following. So, like one is given as input, um, like all evaluations of a univariate polynomial over some interpolating set. Okay, so that is if we're referring to degree D univariate polynomials, actually any set of D plus one inputs is an interpolating set. Meaning if I tell you the outputs that the degree D polynomial should take at each of those inputs in the interpolating set, I am uniquely specifying the degree D polynomial. Okay, so in univariate Lagrange interpolation, like the input to the interpolation procedure, right, is just a description of the polynomial you care about. It is D plus one evaluations of the degree D polynomial, right? And the goal of univariate Lagrange interpolation is to evaluate that polynomial at a random point. And so univariate Lagrange interpolation, at least the way I present it, is it's just an algorithm to compute that evaluation of the specified polynomial at the requested point, and it runs in linear time. Okay, and so it's sort of it's closely analogous to, like, you should think about this as this description of the polynomial p here in terms of its evaluations over an interpolating set. It's just the way of describing the polynomial. Now, most people are probably more familiar with degree D polynomials being specified in what's called the standard monomial basis, where I give you, the coefficients, C0 to CD. so that if I want to evaluate the polynomial at a given point, I just raise the point to the ith power and multiply by the ith coefficient, and that's how I get the evaluations. So Lagrange interpolation is just considering a different way of specifying polynomials, where rather than being specified by their coefficients in the standard monomial basis, the polynomial is specified by its evaluations over an interpolating set, which I like to refer to as coefficients in the Lagrange basis. Okay, and this so-called Lagrange basis, we discussed last time, and for time reasons, I won't recapitulate it all to you, but basically it replaces powers of the input. Those are the standard monomials, with other basis polynomials, each one of which sort of picks out one of the points in the interpolating set. So that's what we talked about last time. Okay, so today, my main goal is to cover the exact analog of Lagrange interpolation, but not for univariate polynomials, rather for what are called multilinear polynomials. Okay, so I will briefly remind you what multilinear polynomials are, and then we'll discuss Lagrange interpolation for them. So multilinear Lagrange interpolation, and this is sort of the technical underpinnings of like all interactive proofs. So the subject protocol and all things like that. It uses at its core like multilinear Lagrange interpolation. So it's kind of the main technical thing to get comfortable with. And it is ultimately I think it's actually simpler than univariate Lagrange interpolation. It just takes a little bit to get comfortable with because you're dealing with more than one variable. But I think before I discuss multilinear Lagrange interpolation, I think just kind of to take a short break from facts about polynomials. I think first I'll introduce interactive proofs and arguments. Like, what are they? Say a little bit about them. So interactive proofs and arguments, and then we'll dive into this multilinear polynomial stuff. And again, the reason to cover multilinear polynomials and multilinear Lagrange interpolation is because they are kind of the fundamental objects used to build efficient interactive proofs. Okay, so let me pause there and see if anyone wants to ask any questions about the recap or what we're going to do today. Okay. Yeah, so let's talk about interactive proofs first. Now, the term proofs in this entire space, whether you care about snarks or verifiable computing, whatever term you want to use, the term proofs is sort of vague and overloaded. So when I say interactive proofs, I actually mean something very precise, and that is a protocol that operates as follows. So there is an untrusted prover P and a verifier V, and the prover makes some claim to the verifier. And so, I to keep things concrete, I like to think about the following very specific setting. Like, the verifier sends an input X to the prover and asks the prover to tell it f of x, where f is some function, and in practice, maybe often this function will be specified in the form of a computer program. And so the verifier is really asking the prover, hey prover, run this computer program on my data, right? So this x is like the verifier's data, and the verifier is really asking the prover, please run this computer program on my data for me. So this little, picture, is sort of capturing like the prover, and might actually be like a commercial cloud computing provider or something. The idea being that the verifier just has a laptop, so that laptop is like too weak to run the computer program on the data, so it's going to ask Amazon to run the computer program for it, using Amazon's like beefy computer cluster or something. Okay, and so the prover comes back and says, okay, I ran the computer program on your data, and it output some value 42 or something, so claimed output Y, and the verifier doesn't trust that the prover is honest and like really did run the computer program on the data to get Y. So in an interactive proof, the verifier will start interrogating the prover, sending a sequence of challenges and getting a sequence of responses. And so it's interactive. So there's the verifier will send a challenge, get a response, send another challenge, get another response, and this will just proceed round over round, until at some point the verifier stops sending challenges and either like accepts the claim as valid or rejects it as invalid. Okay. So that is an interactive proof, and any interactive proof has to satisfy two requirements. The first is called completeness, which just says that an honest prover that returns the correct answer and follows the prescribed protocol will cause the verifier to accept. So completeness says honest prover will cause the verifier to output accept. Now, in as I'll discuss shortly, like in general, completeness does not have to be perfect, in the sense that you could have protocols where there's a small probability that even an honest prover gets its claim rejected by the verifier. But like in practice, like all of the protocols we use actually have perfect completeness, where if the prover is honest, the verifier always accepts. So let me just qualify. Everything we discuss in this study group will have perfect completeness. And then the security property that interactive proofs require is soundness, which says if the prover, sort of begins with a lie, so it returns a claimed answer that is not equal to the real answer, right? Then the verifier will reject, with overwhelming probability, so with very high probability, no matter how hard the prover works to try to answer the challenges, to compute responses to the challenges. Okay, and so here's the key point, and here's what I meant when I said I mean something very precise here by interactive proof. This soundness notion for interactive proofs is what's called statistical soundness. Another word for that is information theoretic. Okay. And that means that no matter, there's no cryptography here. The prover can't get the verifier to accept by finding a collision in a hash function or anything like that. No, even if the prover spent trillions of years computing like the best possible response to every challenge from the verifier will still catch a cheating prover in a lie with overwhelming probability and reject. And kind of what's going on here, and we'll see examples of this in the coming weeks, is kind of that if the prover starts with a lie, then it'll wind up being the case that for every possible response to the first challenge, the prover will still be left with a lie. And so you go round over round through the protocol, and at the maybe let's say the protocol like ends with a challenge, which actually the prover doesn't even need to know because it's the final message. So basically, like even in this final response, what will happen in these interactive proofs is the verifier is going to like chooses a random value at the last possible second. And since the prover didn't know when it sent the final response what that last random value will be, it's the prover is going to wind up getting caught by the verifier at the end, no matter what. Okay, so yeah, again, interactive proofs have this statistical notion of soundness, where it doesn't matter how much computational power the adversarial provers have. The prover will still get caught in the lie with overwhelming probability. Now, there are other notions of soundness that are important in practice, but the term interactive proof is specifically referring to statistical soundness. And so, in at least in complexity theory, if you ever see the word proof, like that should mean statistical soundness. Okay, but people do get extremely imprecise about this, and so people will talk about ZK proofs, like in practice, and what they'll mean typically is computational soundness. So that this gets confusing, and in the book, I do use the term like snark proof sometimes. But whenever I say snark proof, like it's not a proof. It's not statistically sound. But I think it'll be clear that I actually mean computational soundness, which I'll define in a moment, because of the qualifier snark before proof. Okay, so yeah, again, typically in the book, if you see the word proof, it means statistical soundness. But you do have to be wary, keep your head on a swivel. Like in practice, people will use proof to not mean statistically sound stuff. Okay, let me pause there, see if there are any questions.
So is the difference between statistical and computational soundness what's the difference between proofs and arguments?
Yeah, that's exactly it. Yeah, typically, if something is computationally sound rather than statistically sound, like you should call it an argument. And indeed, that's what the AR in snark means, is argument, which is why it should be clear when I say like snark proof that I really mean an argument. Unfortunately, in the research literature, it's pretty mixed up. Like some people will just say like ZK proofs, and they really could mean either statistical or computational soundness, and you have to like keep reading well into the paper to figure out which one they mean or something. But yeah, like really, like arguments should refer to computational soundness, and proofs should refer to statistical. Again, people don't really stick to that.
So just a follow-up question. So does it mean that the Merkle proof is actually a Merkle argument? Because it's
that's a good question. It sort of depends how you define what's being proved there. So a Merkle commitment is only computationally binding. So a Merkle proof, you could be saying, hey, like I'm proving that I know how to open this commitment to this data. And in that sense, it is a proof. Like, statistically, like like by definition, you're sort of defining the statement being proven as like, I know this authentication path. So hence this is a proof. I know the authentication path. Here it is. But that knowing that path is only meaningful in a computational environment, right? Because if you don't bring in any kind of collision resistant hash functions, which is a computational assumption, then that Merkle root, the Merkle root always has many openings. The collision resistance is what guarantees that any single efficient prover only knows one opening. So yeah, your question is a little bit ill-defined. The Merkle path is a proof that the prover knows the Merkle path, right? But if the prover is computationally unbounded, it knowing a Merkle path like doesn't really imply anything at all. Does that make sense?
Yeah, thank you.
So is it approved to? So is it approved to Merkle argument?
Yeah, so you could kind of put it that way. Yeah, I'm
Wow.
fine with you putting it that way. Although people don't use that term Merkle argument like ever. I just as another example, just to make sure this is coming across clearly. Like there are really important proofs. Like the prover can prove. Well, how do I want to put this? Make sure can prove. Yeah, so a prover can prove it knows, like can efficiently prove it knows, discrete logarithm, like an x such that g to the x equals y. Okay, so this will be like Schnorr's protocol. This will let the prover prove this, like in zero knowledge. If you don't care about zero knowledge, the prover could just provide x, right? And so, Schnorr's protocol is a proof that the prover knows X. Don't worry about what knows mean. Just treat it intuitively. Obviously, if the proof were just X, that would be irrefutable proof the prover knows X. Okay, but if the prover is computationally unbounded, like it's not interesting that it knows X. Of course, it knows X because such an X will always exist in the cryptographic groups that we deal with. So, that's another example, as with this Merkle authentication example, where like you can have like, unconditional proofs, statistically secure proofs that the prover, knows some information, but the fact that it knows that information is like not interesting unless there's computational assumption somewhere because the information is guaranteed to exist always. And so, anyone who's computationally unbounded automatically knows such a piece of information. So that these are contexts where proofs and arguments, kind of the notions get munched together a little, and what's going on is just snarks use cryptography internally, and they're also often used to prove statements about crypto systems. I claim to know a plain text that corresponds to this public ciphertext or something, and so you kind of have that's where all this munging together of statistical soundness and statements that are only relevant in computationally bounded settings arises.
So
one more.
does it mean that in computational unbounded computation, if we are starting, if we are bringing a computationally unbounded party, then this argument versus proof thing becomes quite meaningless, since the argument can be even stronger than proof.
I think the way to think of it is, the notion of an argument like itself only refers to computationally bounded provers. So, is just like neither here nor there if you're considering computationally unbounded adversaries, for whatever external reason, like just arguments just don't make sense. Like, once there's a computationally unbounded adversary, computational soundness is just, not helpful. I guess the way I would put it is the canonical example, like this outsourcing example I gave, where like a cloud computing verifier is asking the cloud to run a computer program on some public data. That's where statistical soundness is like a very meaningful notion. Where the honest prover will like just run the computer program and do hopefully not that much extra work to prove that the claimed output is correct. But then so the honest prover is efficient. The verifier saves a lot of work by not having to run the computer program itself. But then the interactive proof is secure even if the cheating prover spent trillions of years trying to convince the verifier of a false claim. Now, in SNARK design, ultimately, we are going to bring in computational soundness somewhere. So interactive proofs are like a key building block in SNARK design, but you might say, what is the point of looking at interactive proofs if once we sort of turn them into SNARKs, if we're going to use cryptography to do so and only get computational soundness in the end for a SNARK, and there the answer is really just for performance reasons, right? So like again, SNARKs in the end are always only computationally sound, not statistically sound. They use as building blocks some of these statistically sound protocols. The reason the statistically sound protocols are interesting is not so much because they're statistically sound. We really don't care, given that once you turn them into a SNARK, they're only computationally sound. The reason the statistically sound protocols are so interesting is because they don't use cryptography, and cryptography is expensive. For the prover to cache a bunch of data or do a bunch of group operations, that's a lot of work. Those are slow operations for the prover. And so it turns out to be very interesting to study these statistically sound, interactive proofs, not really because we care about statistical soundness in the end, but rather because they lead to really fast provers in certain important cases. Does that make sense?
This is very clear. Thank you very much.
Great. Other questions? Okay. Good. So let's see. Yeah, so let me just define computational soundness, also known as an argument. So this just says that like if the prover starts with a false claim, then roughly like any efficient prover, so any prover that does not basically any prover that's not capable of breaking some cryptographic assumption, meaning like finding a collision in a collision resistant hash function, or computing a discrete logarithm in a cryptographic group where discrete logarithms are believed to require a incredible amount of time to compute. So any efficient prover cannot convince the verifier to output accept, except with tiny probability. Okay, and in both the interactive proofs and the arguments, this probability that like a cheating prover, convinces the verifier of a false statement, typically this probability looks something like 1 over the size of the field you work over. And again, so if you work over fields of size like 2 to the 128 and up, then this probability is like so small that you basically can assume it'll never happen, in the history of the universe or something like that. So that's computational soundness, also known as arguments. Okay. Now some brief comments going back to interactive proofs. So people have looked at very early on. People looked at a lot of kind of variations of the interactive proof model. So they considered a lot of things like, so there's something called public coin interactive proofs versus if you're not public coin, then people call that private coin. In public coin protocols, what that means is like every challenge sent by the verifier is just like random coin tosses tossed by the verifier, which like in practice tends to mean consists of like uniform random field elements or something like that. So in general, you could imagine like the challenge can have be in the form of any message the verifier wants to send the prover. But if the protocol is what's called public coin, then the challenges are extremely simple. They're always just like random field elements or something. And it turns out that, let's see, what other variations do I want to mention before let's see. Sorry, let me pull up my notes. So there's public versus private coins is an important one to know about. There is, pull up the book real fast. Sorry. Yeah, so there's perfect versus imperfect completeness. You know, there's the question of like just how low do we require the soundness error to be? So this probability here. This is like the probability that a cheating prover kind of gets lucky and convinces the verifier to accept, even though the original claim was false. And yeah, okay, so there's some other variations as well that I don't think are worth getting into. And so in the early days of studying interactive proofs, you know, in the mid 1980s, people sort of figured out that like nothing really matters. So like if I give you like in principle before you start studying this question, it may be the case that like letting the verifier toss, you know, send arbitrary challenges to the prover versus these public coin protocols. It may be the case that the private coin setting is somehow more powerful. You know, that like you can have efficient interactive proofs for like a bigger class of problems if the verifier can send arbitrary challenges versus these like uniform random challenges. You know, it also may be the case that like demanding that the honest prover always convince the verifier to accept is somehow limiting, and like, you know, you can't achieve that for some of the problems where, you know, you could have an interactive proof if there was a small chance that the honest prover gets rejected and things like that. And it turns out, you know, if I give you a private coin protocol interactive proof, I can actually turn it into a public coin one. If I give you an interactive proof with imperfect completeness, I can turn it into one with perfect completeness, right? And if I give you an interactive proof where the soundness error is pretty high, say only like a third or something, meaning that a cheating prover actually convinces the verifier to accept with pretty high probability, you know, certainly not cryptographically small, it turns out that by like repeating the protocol many times or like going inside of it and making the field bigger or something, I can, you know, reduce the soundness error from a third down to something cryptographically small, you know, 2 to the minus 128 or something. And so what that means, you know, intuitively is that like interactive proofs, you know, it's the notion of interactive proofs, you know, the notion of them is highly robust, which is, you know, to a complexity theorist, this is like a very good sign that like this model is like really meaningful and like kind of the right model to study. You know, that like little teeny changes in how you define, you know, the model, like what you require from your protocol, don't actually fundamentally change the power of those protocols. Now, yeah, so all of these results went through transformations. Like I give you a private coin protocol, I can transform it into a public coin one that solves the same problem. I give you a protocol with imperfect completeness, I can turn it into a different protocol that solves the same problem and has perfect completeness. But it turns out that like all, you know, like natural interactive proofs, which I abbreviate IPs, you know, just so I don't have to write out interactive proofs 1,000 times, kind of directly have all these nice properties. So they directly are public coin. You know, they directly have perfect completeness. You know, if you work over like a big enough field anyway, they're always going to have, you know, cryptographically small soundness error, etc. So, you know, there are these transformations known where you can take protocols that don't have these nice properties and turn them into ones that do. But like all protocols we'll see will just directly have the properties anyway. You don't have to invoke the transformation. And that's actually nice because the transformations in general actually add a lot of overhead. Now the overhead in theory is not that big, but in practice would actually be like really terrible. So yeah, that's the extent of the discussion I wanted to have about this. I wanted to raise these notions of public versus private coins, perfect versus imperfect completeness and stuff. But then all the interactive proofs we actually see will just be, you know, have all the nice properties we want anyway directly. Um, okay, and the public coin thing is really important, by the way, in Snark design, because this means, the interactive proof itself doesn't use any cryptography. But now if I bring in some really lightweight cryptography, something called the Fiat-Shamir transformation, I can take any public coin protocol and I can turn it non-interactive. So we'll turn the IP into a non-interactive protocol. And I'll say in a second roughly how Fiat-Shamir works, and we'll have a whole session on this, in a month or two. Now, the non-interactive one will not be a proof anymore, so it will be an argument. Right. So Fiat-Shamir uses cryptography, right? So the interactive proof will be interactive, but it will be public coin. And then by using a little bit of cryptography, you can make it non-interactive, but no longer is it a proof. Now it's an argument. Okay. So what Fiat-Shamir does is, in these public coin protocols, the challenges from the verifier are just like random field elements, random coins or something. And what Fiat-Shamir does is it basically has the prover choose the challenges. Now, if you did that in like a naive way and literally just had the prover choose the challenge, like security would be totally out the window, right? The prover would obviously just choose a challenge that, it was like prepared to, answer by, it's like guessing the challenge in advance. If the prover is choosing the challenge itself, it doesn't even have to guess. So what Fiat-Shamir will do is it will choose the challenge by as the output of a cryptographic hash function. So it will like hash, X and the claimed output Y to choose the first challenge, and to choose the second verifier challenge, it'll hash, everything that came before that, like, X and Y and the first challenge, and that will be the stand-in for the second challenge. And, this is kind of a magical way for the prover to choose the challenges rather than the verifier. It cuts out all of the interaction. And it turns out that, basically because, to intuitively to computationally bounded adversaries, the output of hash functions looks kind of random, even though it's the prover kind of choosing the challenges, or like they're deterministically chosen as a function of the previous challenges or whatever. The prover is nonetheless not able to cheat, not able to like use its prior knowledge of what the challenge will be to find convincing proofs of false statements. So that is one reason in Snark design we really, really care that like our interactive proofs are actually public coin. For example, yeah. Of course, also we care that the soundness error of our interactive proofs is cryptographically small, because if it weren't, then once we turn them into snarks, we're not going to have cryptographically small, large security parameters or whatever. So we care about several of these properties, not just for theoretical reasons, but they actually translate to really important things for Snark design. Okay. All right. So that's interactive proofs and arguments. I think that's all I wanted to say about that today. So let me pause here and see if anyone wants to ask any more questions.
I have a question about the very beginning of the picture of the scheme. It starts with input and output X and Y, and then it goes to challenges. I just wonder, for the general case, is it like does it mean like a prover should redo all this computation to get Y on each challenge, or does this general picture mean something else?
Yeah, so I think the most natural setting, certainly to present interactive proofs, is that the input X is known to both prover and verifier. So in this picture, the way the prover learns X is the verifier sends it to the prover. But like in practice, maybe there's some other way that both the prover and verifier have settled on X, right? And typically, how do I want to say this? Actually, there are some settings where if the prover somehow knew Y without directly computing Y, it could actually answer all the verifier's challenges faster than any known algorithm to compute y. We've already seen an example of this, not a very interesting one, but like for Freebugs algorithm it's actually a non-interactive, right? Okay, so let's go. Freebugs algorithm was like, in the picture I drew, it like the verifier will be sending input matrices A and B. The prover would send back the claimed product matrix, and the verifier would, just on its own do a very quick check. So the verifier would do like a linear time check. And based on the check, it will accept or reject. Okay. So in that setting, this is a non-interactive proof, obviously. Like the picture makes it look like there's interaction here, but like if somehow the verifier is only speaking to the prover to tell it the inputs, right? So if the prover just somehow already knew the inputs, then there wouldn't be any verifier to prover message at all. And moreover, if the prover somehow already knew the claimed product matrix, there'd be no need for it to compute it, right? It would just send it to the verifier, that's the proof, and that's it. And we'll actually see some interactive proofs of a similar flavor where, that basically proving correctness of a claimed answer is kind of a low order cost compared to just computing the claimed answer in the first place. So hopefully that answers your question. Now, I'm guessing, however, that a motivation for the question was that in snark applications, you often have the situation where like the fundamentally different, right? Like, in Schnorr's protocol, the prover is claiming to know, P claims to know an X such that, G to the X equals Y. That's one, or, like the prover claims to know a W, such that, feeding W to some circuit causes it to spit out 1 or something. Okay. And now these are funny applications, right? Because, if the prover, computing discrete logarithms is assumed to be hard, right? So like if you if the prover didn't have a reason to already know X, there's no way it's going to compute X on its own in any reasonable amount of time. And similarly, if the prover didn't have some reason to already know the witness W that it's claiming to know here, there's no way it's going to be able to compute W quickly, right? Because circuit sat is like an NP-hard problem. So in many snark applications, right, like the prover is, claiming to know a witness for some NP problem. Because it's an NP-hard problem, the prover cannot possibly compute the witness from scratch on its own. What's going on is that in various applications to cryptography, the prover already knew the witness anyway, right? So like, in applications of Schnorr protocol, the reason the prover knows X is because the prover chose X, right? It chose X, it computed G to the X to get Y, and then it made Y public, and then later wanted to prove that it was the party that made Y public, and proving that is equivalent to proving it knows the X. Right, because no one else can efficiently compute the X, but the prover knows the X because it chose X and used that to determine Y. Similarly, like in a snark where the prover is claiming to know some witness satisfying some property, the prover knows the witness. It doesn't have to compute the witness from scratch. So that's another subtlety that kind of makes it a little tricky to ascertain like exactly what picture I should draw when I'm introducing interactive proofs and arguments. Like the applications kind of just muddy the picture because in a lot of them the prover knows some information that if it didn't know for exogenous reasons, it had no way of efficiently computing on its own. Okay, sorry for the rambling. Hope that was clarifying.
Yeah, thank you.
Okay. All right. Last chance for questions.
So I had a question.
Okay.
I just wanted to verify that the idea of a non-interactive proof only makes sense in the context of a computationally bounded prover, right? Like only helps in that
Yeah,
context.
that is okay. So short answer, yes. Long answer is the following. Okay, how do I say this? Okay, let's look at Frivold's algorithm again. Okay, now Frivold's algorithm has information theoretic security, and it's still useful, right? In fact, you so it's still useful. Like the verifier's check of the prover's claim is much faster than the fastest known algorithm to compute the claimed answer from scratch, and the protocol is information theoretically secure. But what's happening there is the verifier is saving some work, right? Linear, there's no linear time algorithm known to multiply two matrices, so the verifier is saving some work. But the amount of work it's saving is what theorists would call just a polynomial factor, right? And so that's sort of like it's widely believed that non-interactive proofs, and by proofs here I mean statistical. I really mean proof. Statistical security. Can only save the verifier like a little bit. Now, a little bit can still be very meaningful in practice, but a little bit. So like Frivold saves the verifier some time, but not an exponential amount of time. Frivold saves the verifier time. Another notion of savings is like how long is the proof, right? And there's very good evidence that if the prover if the prover claims to know like a W such that it causes some circuit to output one, right? With statistical soundness, whether interactive or otherwise, there's very good evidence. So we strongly believe, there is no shorter proof than just sending W. Right. So like the trivial proof system for any NP-hard problem, the prover's claiming to know some NP witness, is for the prover to just send the witness and for the verifier to check that the witness is correct. And, the slightly non-trivial thing to do would be to then, after the prover sends the witness, if checking the witness is correct is itself computationally intensive, you could then use an interactive proof to, have the prover prove that the witness is correct. But either way, you start by sending the witness. And we strongly, strongly believe that, without cryptography, the proof has to at least be as long as the witness. So, okay, so that way, by now I have very long-winded answers. Without cryptography, we have very, very good reason to believe that, you can either, in terms of proof length, you really can't save anything at all over the kind of obvious trivial proof system. And in terms of verifier time, you maybe can save a little, but not much. Does that make sense?
Yeah, that makes sense. Thank you.
So I have a question about statements that we currently believe wouldn't. So doesn't this second property come from pigeonhole principle in information theory?
No, actually, so this is referring to, so there are statements like the following. There's several papers trying to give evidence for exactly this bullet point here. And they'll say things like, broadly speaking, like suppose there were an interactive proof, and again, even if you allow the interaction, but you insist on statistical security, so there were an interactive actual proof, for circuit sat, or some other NP-hard problem, where the total communication, sent by the prover is lower than the length of the witness. So witness size. Okay, then you get like you can conclude that like something like P equals NP. So not literally P equals NP. So what we actually know is that like it's more statements like the polynomial hierarchy collapses. Don't worry about what that means. This is like something close to P equals NP, but not exactly the same as P equals NP. Right. So most complexity theorists believe that P does not equal NP. And so something intensely surprising would have to happen in order for there to be interactive proofs where the proof is like very, very succinct, meaning shorter than the size of the trivial proof system where the prover just sends the witness to the verifier. Something to point out also is that even if we, shockingly live in a world where P equals NP, at that point, like in some sense, there's not much point to having a prover because the verifier at that point could efficiently compute the claim witness on its own, right? If P equals NP, then it's not actually hard to compute this witness. So, what's the point of having the prover in the first place? These statements are like, they're actually much more sophisticated than just like the pigeonhole principle. It's like, if there were a non-trivial statistically secure protocol for NP hard problems, non-trivial meaning in terms of proof length, we would, I don't know, we live in a very, very different world than we think we live in. Did that make sense?
Yes, thank you.
So,
Let me have also a very quick one. It's most to the session about Fiat Chimere, but is it true that when we go from interactive protocol to non-interactive, we always will have only one so-called, so could be said, interaction? And is it true that when we need more security, we can simulate more interactions, but as long as they are wrapped in one Fiat Chimere construction? I mean, no parallel Fiat Chimeres.
Yeah. So, okay, that turns out to be like a very loaded question, actually. So, I'll try to keep this short since I've eaten up, most of this session with such rambling answers already. Typically, what happens in practice is if you work over a big enough field, you're just going to get cryptographically small soundness error, and everything is good. Now, working over a big enough field can be expensive, performance-wise for the prover or something, and like a great deal of SNARK research, today is devoted to addressing those performance challenges that come from working over a big field. Now, you could work over a small field, which is not going to give you cryptographically small soundness error, and then try to amplify the soundness error via repetition. Okay. It turns out that if you do any kind of repetition and apply Fiat Chimere, you're asking for trouble. So I don't want to say, dive into more details than that, but like if you were to do repetition sequentially and you apply Fiat Chimere, you might as well have not done the repetition at all. It does not add security. And even a lot of people think if you do the repetition in parallel, like that should be okay. It turns out it's not. Okay. So people should just avoid repetition effectively is sort of a message to take away. Now coming back to another aspect of your question, I know that all my answers are way too long, but a lot of really important interactive proofs actually, even if you do work over a big field, they involve a lot of rounds. And this is one of my like hobby horses is most of the popular snarks today, the part of the snark that like corresponds to an interactive proof, sometimes they're not literally interactive proofs. They're something called polynomial IOPs that are related but not the same. They don't use a lot of interaction. Okay. But as a result, the snark then has to use a lot more cryptography, to, yeah. So this gets a little hard to explain, but like if you don't want to use any cryptography, like it's actually known you need a lot of interaction to save the verifier work. There's a precise statement here, like if right here you can take any k-round interactive proof and turn it into a one-round interactive proof with how do I want to say, with a bounded increase in verifier costs. Okay. Now, in practice, the increase is significant. Basically, if the verifier runs in time t, then to get rid of the k rounds and turn to the one round, the one round verifier might actually run in time t to the k. So that is a big blow up. But like if k is like 3 or 5 or 10, it's still just a quote polynomial blow up. And so it's actually known if like unconditionally, if you don't allow any cryptography, then in order to like save the verifier a super polynomial amount of work, you need many, many rounds. You need a super constant number of rounds. Okay. And so many round interactive proofs are completely needed if you're trying to like really minimize the amount of cryptography that the prover uses in your final argument system. So to finish the rambling, I'm sorry, I said it wasn't going to be that rambling, and then it was. There are a lot of snarks today that like don't use many rounds, and if they work over a big field, they're sound and they don't use many rounds. Whatever. But I think people should be actually using snarks that do use a lot of rounds in order to minimize the amount of cryptography that the prover has to do. And then you'll remove all the rounds with Fiat Shamir. Okay, so sorry for the rambling. There are a bunch of aspects to your question.
Thanks a lot. I guess we will have this in future sessions.
Yeah. We'll talk about all of these things in a lot more detail in the coming weeks.
So, hello, Professor. From the line that's there on the screen, that if P claims to know the witness such that hard problem or circuit satisfiability is satisfied, from that statement, is it correct to infer that you're trying to say that for Samcheck protocol, the transcript size is actually the witness size?
Yeah. So the way to think of it is, let me think about this for a second. So, yeah, if you just use Samcheck and no cryptography for something like this, like the way you would do it is, and I just had discussion about this in the Discord chat. So if you haven't had a look at that, feel free to take a look at your leisure. But so the way to use Samcheck and no cryptography for circuit sat is to have the prover send the witness to the verifier, right, and then use Samcheck to prove like interactively, that C of W equals Y. Okay, and this is so this still has like this is not any more succinct than the trivial proof system where the prover sent W and the verifier evaluated C of W on its own. Okay, because the prover is sending W. But the verifier is saving work, so V is faster, than evaluating C of W on its own, because it used Samcheck to offload the work of the prover evaluating C on W. It offloads that work under the prover rather than doing it itself. By virtue of sending the witness to the verifier, we would call this, a non-succinct proof. The term succinct means somewhat different things in different contexts, but in snark land, this would be considered non-succinct because the proof is as big as the witness. Now, this answer might be a little bit confusing to you because there's this famous result called IP equals P space, which says not only can the prover, well, how do I want to say it? Okay, so I'm just going to switch rooms and then wrap the session up in the next 10 minutes since since my room got taken for a meeting and then I myself have a meeting shortly. So yeah, so this proof would involve like the proof size here coming from some check is just like logarithmic in the circuit size. Right. So the non-succinctness is coming in just because of the prover sending the witness to the verifier. Everything after that is what we would consider succinct. In a snark, if you actually wanted succinctness, rather than the prover explicitly sending the witness to the verifier, it would cryptographically commit to the witness. And that's where you would get proofs that are even shorter than the length of the witness coming in, but you don't have statistical soundness. Now, this result at IP equals P space, you might be a little bit confused because that involves the prover. How do I want to say that? You might. Well, okay. So the way I'll put it is the protocol on IP equals P space is not more succinct than what's above. So there, I guess we'll talk about that in a couple weeks. And so just there's no contradiction between the fact that IP equals P space and the assertion that this proof here it has the prover send the witness in full to the verifier. Was that helpful?
Yes, sir. I got what you're saying.
Great. Okay. Good. So yeah, let me just summarize some of these rambling things I said, not all of which are discussed in the book. So let's see. So the book does discuss that if you want let's see, if you want to save the verifier a lot of work. So the summary here is you want to save the verifier a lot of work compared to what it could do without access to a prover, and you want statistical soundness, so an actual proof. Okay, you need a lot of interaction. Like more than constant, like logarithmically many rounds of interaction are up. Okay, and then even then, if you have statistical soundness, the proof, the total communication will be at least as big as the witness that the prover is claiming to know. Okay. And and also, by the way, there will be non-zero soundness error. So you can make it cryptographically small, but not zero. And so no matter how much interaction you allow, if you insist that the soundness error is literally zero, that an adversary has absolutely no hope of convincing the verifier to accept, no matter how lucky it gets, you will never do better than the trivial proof system where the prover just sends the witness to the verifier. And of course you can get an argument where the quote proof, but it's no longer statistically secure because it's an argument, is shorter than the witness. and there's no interaction. Okay, but like the way that always works is the prover commits to the witness cryptographically. Yeah, but this needs cryptography. So it's like the commitment will be like one hash value or one group element, and there will always be like many ways to open the commitment. But a computationally bounded prover better only know one way to open the commitment, and then you wind up proving that one way to open the commitment is actually a valid witness for the prover's claims. So this needs cryptography, and hence you give up statistical security, and you get an argument and not a proof. So that is the 3 bullet point summary of I think the main takeaways of most of the discussion today. And as in typical form, we did not even get to multilinear Lagrange interpolation, but I think that's okay. So let me pause here and see if there are any follow-up questions.
I wanted to ask, because you mentioned that people should avoid repetition at all. But you also mentioned that we need protocols that have more rounds of interaction.
Mm-hmm.
So can you clarify what's the difference between them? Because maybe I didn't understand what you refer to as repetition.
Yeah, sounds good. I guess I want, for, the broader audience, this will be in the weeds a bit. So if we're past the hour, and if you or don't want to go in the weeds, I think you can just drop off. Just heads up. But yeah, it's a great question. So okay, let me just say some things about Fiat Shamir security, I guess, right now. Okay, so in general, if you apply the Fiat Shamir transformation, so if you apply the Fiat Shamir transformation to a protocol, with k rounds of interaction, if k is big, you can have a massive loss of security. And so let me tell you exactly how much security you can lose. So it's like if the soundness error of the interactive thing, so soundness error pre-Fiat Shamir is 2 to the minus lambda. Post Fiat Shamir, right? The bits of security might be as little. So this is like lambda bits of security. So you might have as little as lambda over k bits of security. Okay. And so even for like k equals to like 2 or 4, this could be catastrophic, right? Like if you're working over 128-bit field, a lot of projects today are working over even smaller than 128-bit fields, and like I really think they shouldn't be. But so let's say you are working over 128-bit field, and you lose, a factor 2 in security. Now you only have 64 bits of security. That is totally insecure. Like that. 2 to the 64, hash evaluations like you could do on like a, even a laptop maybe. I'm not sure. It's certainly on like an Amazon cluster, like in that's not secure. So this in general, Fiat Shamir does not preserve security. Okay, but fortunately, for many K-round protocols, there actually is no loss of security. So post Fiat Shamir still has lambda bits of security. Okay, and so most of the protocols people do want to use in practice actually have this nice property that like you can apply Fiat Shamir, there's no loss of security. And so this is known for like the SumCheck protocol. A sort of Fiat Shamir friendly, Fiat Shamir secure. It'll have logarithmically many rounds, but you Fiat Shamir it, and there's essentially no loss of security. Also, Fry has logarithmically many rounds, and it's now known that if you Fiat Shamir, you have essentially no loss of security. Both of these statements actually were not proved that long ago. For SumCheck, it's not really that hard to prove. For Fry, it's fairly, there were 2 whole papers on it that independently did it. So this was just like last year or something. And so, people spent years saying, Fry is secure in the random oracle model, meaning Fiat Shamir secure. and no one had actually proved that until like 2 years ago. And so, I think the general sense of people in the community is, hey, like anything you actually want to use, like just fiat Shamir, it doesn't matter how many rounds it has, and you're good, like it'll be fine. And actually, this is not true. And so let me go back to how security can be lost. Okay, so there's a canonical example of something that's not fiat Shamir secure, and that is the following. Say you have an interactive protocol, okay, with soundness error like a third or something. So not cryptographically small. Okay, so like the most naive way to try to drive the soundness error down is to just say repeat the protocol, k times in sequence. So like run it once, then run it, finish running it, then run it a second time, then run it a third time, and so forth, and then like accept only if all k runs accept. All k runs accept. Okay, and this will work interactively. So now for the k-fold repetition, the soundness error is 1/3 to the k. Let's change 3 to 2. That's okay. Great. So now if k is 128, you repeat it 128 times. You're cryptographically secure. Okay. If you apply fiat Shamir to this, it has like no security at all. Okay, and people do know this. This is this does not need a public service announcement. Everyone kind of already knows this. And I'll briefly describe the attack, but where people kind of have gone wrong is to think that like people tend to think this is the only situation where fiat Shamir is not secure, is this sort of sequential repetition situation. And in fact, there's another really important case that that's also attackable after you fiat Shamir. So let me just briefly sketch the attack, and then I'll discuss the other situation, and then then we'll be really done for the day. So here's the attack on the fiat Shamir thing. So a fiat Shamir proof would basically be like okay. So let's say the protocol with soundness error half has one round. So the verifier sends a challenge, the prover sends a response, and then based on the response, the verifier like accepts or rejects. Right. So it's a one-round protocol, soundness error half, but then we're going to repeat it 128 times in sequence, except only if all 128 runs accept. So after fiat Shamir, let me say, is it easier to think about the response coming for? Yeah. Okay. Let me actually reverse the order. That I think it's just easier to illustrate. So let's say a message from the prover, and then a random challenge is sent in response. Let's okay. So once you fiat Shamir it, like what's a convincing proof? It's like a message for the first run, so that if I like hash the first message, the verifier accepts, followed by a message for the second run, so that the second repetition, so that if I hash the first two messages to get the challenge for that repetition, the verifier accepts, and so it's just a list of 128 messages, each of which sort of hash to a challenge, causing the verifier to accept that message. Okay, so what the attack is, it's called a grinding attack. So the prover is first just going to do a linear search over message ones, so this is called grinding. So you grind over the message for the first repetition, right? So like maybe the prover tries some message and sees what the hash is, and the verifier actually rejects the message based on that that challenge, and so the prover says, okay, that didn't work out, let me just try another message. And so it tries another message and hashes it to get the verifier challenge, and if it can just keep going and going and going until it finds a message that does hash to a challenge, causing the verifier to accept. And because the verifier's acceptance probability in each run of the protocol is a half, it in expectation it only has to try like two messages before it finds a good one. Okay, and the key point is like now it's done, like attacking that first repetition. So it can just fix that message it found, like good for the attacker, bad for the verifier, and move on to attacking message 2. So it attacks one round of the sequential repetition at a time, one repetition at a time. And the point is, it like doesn't have to get lucky, doesn't have to find a successful message for all 128 repetitions all at once. It can kind of attack the first repetition. Once it's done, it's done with that repetition, move on to attacking the second repetition, and so forth. So that's the grinding attack. And yeah, so people know this attack very well. And so in Snark design, like no one will ever take an interactive protocol or even a non-interactive one and like repeat it, many, many times sequentially and apply Fiat Shamir. Literally the repetition like does not help at all after you Fiat Shamir it. So the subtlety, which, I think I'm trying to give this public service announcement over and over again because people keep running into the problem is the following. So you might think, well, okay, let me just try not doing the repetition sequentially, right? So let me run the protocol once. Let me if I have this protocol with like soundness error half, like rather than running it to completion, once, then run it again, then again, and so forth. That's sequential repetition. We know that's not secure. So what they'll say is like run it in parallel. What that means is, and it gets a little, so you got your prover and your verifier. And, remember the base protocol is just like a message and a challenge. And the parallel repetition would be, you now have a prover and a verifier. And it's like, you send M1 and M2, and then the verifier picks, I guess it would be one challenge for both. Let's say they're K repetitions. The verifier picks, I think it would pick all K challenges, one per repetition. And like accepts. So say the challenges are, C1 to CK, accepts only if, M1 leads to acceptance on challenge C1, M2 leads to acceptance on challenge C2, and so forth. MK leads to acceptance on challenge CK, right? And this is what it means to do parallel repetition if I'm not screwing something up, which I always might be. But so rather than like running the protocol to completion 128 times, one after the next, instead we run 128 copies like all at once. And so there's still only two messages. They're just gotten 128 times bigger. Okay. And this, many people think is secure. If you Fiat Shamir this, there won't be like any loss of security. And that is not true. What now the attack does not apply actually in the two message case. So if you actually do parallel repeat a two message protocol and then Fiat Shamir it, that would actually be okay. But if your original protocol had many rounds, then you have a big problem. And what's going on is, how do I want to say this? Okay, you could say that the challenge with sequential repetition, or the problem with sequential repetition that made it insecure once you Fiat Shamir it, was the repeated interactive protocol had many rounds, 128 rounds. Okay, and that's why the grinding attack was able to work, because you could kind of attack each round one at a time, or sorry, like each round could be used to attack one repetition of the protocol. So the first round could be used to attack repetition 1, the second round could be used to attack repetition 2, and so forth. Okay, now say you have like a 2-round protocol. It has 64 bits of security. That's not cryptographically small. So you repeat it twice in parallel. And then, to make the security to make it have 128 bits of security. And then apply Fiat-Shamir. Okay. This turns out this is not secure. This still, the Fiat-Shamir thing still only has 64 bits of security. Okay. So it's as if you didn't repeat it at all. And the same attack works. So what's going on is, the resulting, the repeated protocol has two, there's like 2 repetitions and 2 rounds. And so, I'm waving my hands a lot here, but like once you Fiat-Shamir it, you can kind of use the first round to attack repetition 1 and the second round to attack repetition 2. And it took, you're only going to need time like 2 to the 64 to use the, to successfully attack repetition 1 with the first round. And you're only going to need time about 2 to the 64 to successfully attack repetition 2 with the second round. And so, for that reason, I think like whenever, whenever using Fiat-Shamir, do not use repetition to amplify soundness error, before Fiat-Shamiring. Just don't do it. Just like work over a bigger field so that without any repetition, you have 128 bits of security, and then apply Fiat-Shamir to that, no repetition. And, again, like it is okay, unless the protocol, the so-called base protocol that you'd be repeating is 1 round, 2 messages. Okay. So, if the base protocol is 2 messages, it turns out everything's fine. You can do parallel repetition and Fiat-Shamir. But as soon as you have even 2 rounds in that base protocol, it doesn't matter if you repeat in parallel or sequentially, you're still going to have a significant loss of security when you apply Fiat-Shamir. And the attack is like a known straightforward attack. You use kind of once you Fiat-Shamir, you kind of use round 1 to attack repetition 1, you use round 2 to attack repetition 2, and so on and so forth. Okay, so feel free to ask follow-up questions, but that was kind of a preview of Fiat-Shamir, which we'll cover the details of in a few weeks, and very subtle things that come up when these repetitions, they do amplify soundness error in the interactive setting, but as soon as you apply Fiat-Shamir to remove the interaction, you potentially have major security losses. Okay, other questions? All right. Well, hopefully I'm still on this call after that 20-minute rambling overview. So next week is SBC. So I might want to wait. So let me know if you want an off week. Like put that in the chat or DM me. My inclination is to have it be an on week. And just expect a smaller crowd. But I'm very open to just having it be an off week, if enough people want that. If we do have it be an off week, that some people have told me they'd be interested in just having a discussion on your own without me there. And someone's volunteered to lead that discussion. So just let me know. Like, do you want an off week with discussion, or do you want an on week despite it being SBC? And I'll decide, say by tomorrow. Thanks for bearing with my rambling. As always, hope it was interesting. If you do have follow-up questions, I can hang out for 1 more minute. Otherwise, I will either see you next week or the following week, depending on who DMs me.